Hi, my name is Paul Hicks, and today I'd like to talk to you about ruthenium catalysts that are involved in the formation of 1,5-triazoles and 1,4,5-triazoles. To begin with, I'd like to show a general reaction diagram that shows the substrates involved and what the final product would look like. To begin with, you start with an alkyne, which has a triple bond. You add that to an azide, which has 3 nitrogens. You put it in the presence of a ruthenium catalyst, and you get your 1,5-disubstituted triazole. The R2 group is on the nitrogen, which represents the first position, and the R1 is on the carbon, which represents the fifth position. What is R1 and R2, and why are we using ruthenium? There's the general reaction diagram again that shows the 1,5-disubstituted triazole. R1 and R2 could generally be any hydrocarbon chain or any carbonaceous material. Normally they have a benzene ring or an aromatic substituent on them as shown below, and that substituent has an X group on it, which can be really anything, a halogen, more hydrocarbons, or more aromatics. Why are we using ruthenium? Below we've shown a terminal alkyne, and there's an internal alkyne. The difference is that the internal alkyne is sandwiched in between two carbonaceous chains. The ruthenium catalyst is capable of interacting with not only the terminal but also the internal alkyne. Click chemistry can be characterized basically by two reactions, the copper catalyzed azide alkyne coupling and the ruthenium catalyzed azide alkyne coupling. In the copper catalyzed reaction, you get a 1,4-disubstituted triazole. You can see that the R2 is on the first position by the nitrogen and R1 is on the fourth position by the carbon. Reacting with copper will only give you the 1,4-disubstituted triazole, so we can say that that reaction is regioselective for the 1,4 position. In the ruthenium catalyzed reaction, we can get a 1,5-disubstituted triazole, or we can get a 1,4,5-trisubstituted triazole. If the ruthenium interacts with the terminal alkyne, we would get the 1,5-disubstituted. If it interacts with the internal, we get the 1,4,5-trisubstituted. That's a major difference between the copper and the ruthenium, and because the ruthenium can interact with not only the internal but the terminal, it opens up the scope of the reaction to include many more substrates, which makes it much more useful as far as synthetic schemes are concerned. Why do we need ruthenium? This image shows a general reaction mechanism or a proposed hypothetical mechanism for how the ruthenium catalyst in black interacts with your substrates. In red we have the alkyne and in blue we have the azide. In phase 0 we have both of the substrates entering into the same reaction vessel with the ruthenium catalyst. In phase 1 we have both of them complexing with the ruthenium catalyst so that they can be brought closer together and the reaction can begin. In phase 2 we see that some of the red alkyne bonds are being broken or dislocated to join with the azide bonds in blue. In phase 3, we see that we have the characteristic triazole product, and right after that we see that the triazole product dissociates from the ruthenium catalyst to begin the process over again. The ruthenium catalyzed azide alkyne coupling was first proposed as a complementary reaction using ruthenium to the copper reaction in 2008 by Bohren. The most effective complexes involved are pentamethyl cyclopentadienyl ligands which bond to the ruthenium. The main purpose of these are just to stabilize the ligand or the ruthenium's metal center to make it more reactive. You can see that that is the pentamethyl cyclopentadienyl molecule. You put that with the ruthenium and you get this structure to the right. This structure just illustrates what the actual catalyst looks like in solution, and it shows a pretty stable molecule. What's special about either one of these reactions, the ruthenium or the copper catalyzed reaction? Both of them show a high yield in that whatever products you put in, the azide and the alkyne, you're going to get a lot of your triazole out of it. That's always a beneficial aspect of a reaction if you have a high yield. High atom economy simply means that whatever actual atoms you put into the beginning of the reaction as a substrate, all those atoms are being used up to form the product. In some reactions with low atom economy, you see that the atoms you put into the substrate as a substrate are not used to form the product and are wasted. These reactions show a high atom economy. Both reactions show little waste, as I said before with the high atom economy. Also, neither reaction really needs any external stimulants as far as energy or heat or other molecules as substrates, really all you need is the azide and the alkyne. You put them with the catalyst, you wait a while, and then you get your product. Both of them are highly regioselective in that either reaction that you choose to do, you're either going to get the 1,4, the 1,5, or the 1,4,5 substituted triazoles. Those are pretty much the only options given the reaction conditions. That has to do with high yield, high atom economy, and little waste. Also, to note, both reactions can be solventless in that you don't have to add a solvent like water or an alcohol or some other sort of organic compound to help the reaction proceed. All you need are the two substrates. Why does this matter? Carbon coupling reactions are very important reactions because they are the building blocks and help create most of the organic products that are used in industry today. The problem with carbon coupling reactions is that they're difficult to achieve because of the bonding characteristics between carbon and carbon and carbon and hydrogen. They're very stable bonds, which means that they're not very reactive. So reactions that can capitalize on other reaction conditions to help bind two carbons together is always a highly sought after reaction. As you can see in this reaction, you're forming carbon bonds in the form of a 5-membered ring that's aromatic. Both reactions, especially the ruthenium reaction, is highly regioselective. Both of these can be involved in biological experiments. For example, when you're trying to find things that inhibit enzyme activity, you need to be able to react molecules in situ, or what that means is in biological conditions. It's hard to mimic biological conditions when a reaction needs a lot of solvent or it has to have a lot of external energy supplied to it. The cool thing with these reactions is, like I said, they're solventless and they don't need any type of reaction. So it's easy for researchers to mimic biological reactions to show, different types of molecules that can inhibit enzymatic activity. These triazoles are sometimes used as building blocks for the synthesis of new sophisticated ligands that are even more complicated than the triazoles. That uses carbon coupling reactions as well. Triazoles have also been shown to have antifungal properties. If you have any more questions, please feel free to contact me, Paul Hicks, at the email listed below or by the cellular phone number. Thank you for your time and consideration.